Kinetic reactions can be viewed both as chemical events and thermal events. What is the difference between these two? This will be briefly explored in this podcast. In one sense, the chemical kinetics is a means to the end. The chemical process provides the means to produce thermal energy. For many forms of modeling, the major concern is how much energy the species produced when they react. Here, global reactions of a fuel going completely to products is the main concern, along the global thermal properties like adiabatic flame temperature of a fuel and oxidizer and the energy content of a species. When a combustion process is viewed as a thermal event, then all of the chemistry that occurs to produce that thermal energy is of secondary importance. In many combustion problems, the chemical process is very fast compared to other processes, for example molecular diffusion. In this case, the chemistry can be viewed as before the fuel and oxidizer and after the complete products. What happens in between is too fast to distinguish. For example, one form of tabulation used in engine simulations is that it's simply the ignition delay time and the temperature profile. There is no information or detailed information about the chemical process. However, there are examples when just knowing the thermal characteristics is not enough. This is especially true, for example, when the concern is more for efficient combustion leading to less emissions. In order to truly understand the origins of the emission species, detailed chemical models involving the emission species and their precursors are needed. Another example is the HCI engine, whose combustion is steered by the chemistry of combustion and operates under the low temperature conditions, where the consequences of the negative temperature coefficient predominate. Traditional methods, using very simple chemistry, often does not give enough chemical detail to adequately model the chemical sources and consequences. When combustion is viewed as a chemical event, then the complex networks of individual reactions and intermediate species have to be considered. Understanding the complete chemistry gives a better picture of, for example, the rate of combustion of a process, the source of thermal energy, and the origins of harmful emissions that could arise. Tracking the behavior of individual species under a variety of conditions and understanding these processes can give insight on how to improve the efficiency and determine, for example, under what conditions and additives can be harmful emissions can be diminished. Kinetic models within combustion can range from complex chemical models to simple thermal models. The key to modeling is figuring out the balance between getting as much of the right information, meaning the properties you are interested in, out of a calculation, with lower computational power that you have available to you. Computational modeling, as with all forms of modeling, is essentially the art of figuring out what you can ignore. But to make intelligent decisions of what is not important, the process has to be understood. In combustion kinetic modeling, the days are over when one can view kinetics as a simple, fast event. This means that learning about kinetics is not just a theoretical academic exercise. It is actually an industrial relevant necessity.